Torque challenge problems. Number 1. Which is better for prying open a stuck lid off a can of paint? A long screwdriver or a short screwdriver? So here we have the short screwdriver in place ready to pry off that lid, and the long screwdriver. If we notice, this paint can lid is going to need to rotate in order to open, and the pivot point will be right here. As the paint can lid rotates in this direction, the screwdriver is going to rotate in this direction. Noting that there's a certain amount of torque that will be necessary for this paint can lid to rotate. So when we apply a force here at this lever arm distance, this will have to be a much larger force than if I apply a force here on the longer handle at a much longer lever arm distance. Both screwdrivers will need to apply the same torque, but if it were my choosing, I would want to apply less force to get the paint can lid to rotate. Challenge problem number 2. Two children amass 35 kilograms and 55 kilograms sit at the ends of a 3-meter long playground teeter-totter. Where should the fulcrum be placed for the children to balance? Conceptually, we know that each kid is going to have to apply a certain amount of torque to the teeter-totter. For these torques to be balanced, we would probably guess that the fulcrum would need to be placed towards the larger mass kid. So here's a conceptual guess to put the fulcrum right here. Let's compute those torques on the left and on the right. So let's say the torque on the left equals the torque on the right, and that'll be force 1 times L1, and we can write L1 in here as the distance from the 35 kilogram kid from the fulcrum, and L2 will be the distance, lever arm, of the 55 kilogram kid to that fulcrum. Let's put in the numbers we know. So here we have the mass of the first kid times G times that lever arm equals the mass of the kid number 2 times G times the lever arm 2. Let's also note that we don't know L1 or L2, but we know that the sum of L1 plus L2 is going to be 3 meters. So for L2, that will be 3 meters minus whatever L1 is. So we'll put that in here for L2. So we have 343, which is 35 kilograms times 9.8 times L1, and then 55 kilograms times 9.8, which is 539 times 3 meters minus L1. Let's distribute, and we'll collect like terms and solve for L1. So this gives us 343 L1 equals 1617 minus 539 L1. Solving for L1, we get 1.83 meters. And hence L2 will be 1.17 meters. Challenge problem number 3. A 350 Newton woman stands at the right end of a diving board of length 3.9 meters. The board has negligible mass and is bolted down at the left end here, supported by a fulcrum 1.4 meters away. Find the forces F1 and F2 that the bolt and fulcrum exert on the board. This is an equilibrium problem, so we know that the sum of the forces will be equal to 0, as well as the sum of the torques. Since it's also equilibrium, we can choose any axis to be the pivot point. So we can choose the bolt or the fulcrum and measure our torques from there. I'm going to choose the bolt and write out our torques. So the net torque is going to be F2 times L2, this force times this lever arm, minus this force of weight times this lever arm here. Notice we have a positive torque here and a negative torque here, so that's why we need to subtract. That net torque is then 0. So F2, which we don't know, times 1.4 meters minus 350, which is the weight of the woman, times 3.9 will give us a force 2 of 975 newtons. We then look at the net forces being equal to 0. F1 and the weight are negative, so we'll subtract those, and F2 is a positive force here. So let's put in F2 that we just calculated from balancing our torques and the weight of the woman to find F1. So solving for F1, we get 625 newtons, that's the force exerted on the bolt, and then also compared to force 2, which is 975 newtons, the force provided by the fulcrum.